Hello everyone, welcome to my channel. In this session I'll talk about one of the often observed issues in SQL Server, which is latency in AG synchronization. In this session you will not only learn how to troubleshoot, but also you will deeply understand how synchronization works internally and how this latency happens. Let's get started. First, suppose we have AG cluster with two nodes. Client is connected to listener name and committed update transaction. The request goes to primary replica's CMD parser where the query is checked for syntax mistakes. After the parsing and binding, the hash of the query is generated, and that hash is checked against the plan cache in the buffer pool to determine whether a suitable execution plan already exists or not. So, if the plan cache exists, it is passed to query executor component to execute the query. Okay. After getting the plan, how does query executor executes the query? For this, it first connects access methods component. This component is the interface through which data is retrieved and modified. Before any change to the data, SQL Server follows write-ahead logging and logs the data change in transaction logs first by connecting to Transaction Manager. Now, the whole story of data synchronization begins. When Transaction Manager gets data change query request, it first catches the log in the log cache. Then, this cache is flashed to disk. At the same time, in parallel, log cache is pushed to log pool to send to secondary replica. From log pool, logs for each database is captured and sent to the corresponding partner replica. This capture process runs continuously as long as the availability replica is connected and data movement is not suspended for any reason. Finally, the messages in each database replica is sent across the wire to the respective secondary replica. We have only one replica here, so primary has only one queue and sends the data through this queue. Afterwards, the secondary replica receives caches and flashes the data to disk. After the log flash, an acknowledgement is sent back to the primary replica to the Transaction Manager. Transaction Manager sends this acknowledgement back to access methods. After getting the log record confirmation, access methods firstly submits the related request methods to buffer manager, which changes the data in the buffer pool. Until now, we finish it with recording logs in transaction log, okay? Now, we will switch to changing data. Again, important point is buffer manager does not change the data in disk directly, but only change the data in the buffer pool, in the memory I mean. If the page is not in the cache, buffer manager does not bring the data from disk. Instead, buffer manager gets the page from the database on disk, puts it in data cache and passes the results to access methods. Then access methods sends confirmation back to the client. Okay, now your transaction finished. One important point also here, in the secondary replica, after the log is hardened to disk, there is a redo threads, which apply these logs to data disk. Okay, this is a background process. So we understood the whole query execution flow in AG cluster and how AG works internally. Now let's switch to latency in this process. Latency might happen in any of these steps. Luckily, we have performance metrics to track if you observe latency in AG synchronization. We can use performance counter and extended events to measure the performance. Let's talk about performance counter first. To measure the volume of logs being flashed to disk, we use performance monitor counter called log bytes flashed per second. This counter is available from both sides, primary and secondary, and it should be close enough. If flashing per second in secondary is lower than flashing per second in primary, synchronization latency happens due to slow disk performance in secondary. The second important metric is bytes sent to replica per second and bytes received from replica per second. These metrics represent volume of data being sent and received through internet. Bytes sent and received should be very close to each other. If there is a lag, this indicates network latency, which increases synchronization latency. There is another important performance monitor counter called flow control per second in both primary and secondary. Always-on availability group has flow control to avoid excessive resource consumption. When number of unacknowledged messages reaches 8,192 per availability replica or 11,200 per availability database, the sender stops sending messages. For example, primary is sending transaction log messages to the secondary replica. If this secondary replica does not acknowledge 11,200 messages for specific database, primary stops sending transaction logs for this database until secondary acknowledges and this number goes below threshold. Sending resumes afterwards. Why might this happen? Because the receiver is slow to acknowledge. Maybe a receiver is under some kind of pressure. This often happens because of I/O bottleneck, high CPU, or other resource contention in the receiver side. Also, slow network or packet drops also can lead to increased unacknowledged messages. So we can use flow control per second metric to measure how many times flow control has been initiated per second. If flow control in primary side is bigger, it means secondary is slow or there is network latency. If flow control in secondary side is bigger, it means primary replica is slow to acknowledge messages or there is a network latency. Let me show you the metrics with a real example. I have primary and secondary AG replicas. First, I create performance monitor by running this command in primary and secondary. Then we start these counters. So I started the collection. Let's wait around 10 minutes. Okay, after around 10 minutes, let's stop the collection. The output has been generated in the temp folder. I put two of these output files in the same location. Now, let's start checking. First, let's start checking network latency with bytes sent and received per second. I add counters from both servers. As you can see, bytes sent from primary is nearly being received on time by secondary. They are overlapping, right? Nearly all the time. If you see significant difference here, this indicates network latency. Let's check the number of flow controls per second. As you can see from both sides, it is 0. It means there is no any latencies being observed. This also indicates very good synchronization performance between the replicas. If flow control is high in primary, this indicates secondary is slow in syncing. If secondary side flow control is higher, this indicates slow sync from primary side. Finally, let's have a look at disk performance. You had better select only our target AG databases. Here, mine is TestDB. You can see disk performance from both sides are nearly equal, indicating good I/O performance. This has been initial analysis with performance monitor metrics, which you can refer in your case scenarios. Performance monitor counters are good to investigate and often help to find cause of the latency. However, sometimes we may need more detailed logs. In this case, we use extended event logs. By using extended events, we will be able to track each transaction log block synchronization steps. Okay, so let's explore event names. First, when transaction is started to be synced, HADR log block group commit is recorded. This is the starting point. Next, events are related to disk performance. We can track when specific log flush started and completed in each replica. When logs are pushed to log pool, HADR block push to log pool is recorded. Next ones are related to capturing log blocks. Mode 1 is logged when capturing log block. Mode 2 is before queuing block to message queue. Mode 3 is when message is ready to be dequeued and ready to be sent. Finally, mode 4 is when the block reached transport layer and just before sending to secondary. Now, when log is sent and reached to secondary, there are receive and sending events. By using timestamps of these events, we can check network performance. Then, after it reaches the log cache, this log block is recorded. After flushing completes, acknowledgement is sent back to primary, and the timestamps of this acknowledgement is also recorded with these events. As you can see, with these events, we can track when acknowledgement is sent and when received by primary. Let's create extended event to trace these AG sync events. I run this query for this. As you can see, I'm adding mentioned events and also some useful events. I start the trace. Then I run one insert query and insert one row of data to the test table in TestDB database, which is part of AG. After the insert, let's stop the trace. As you can see, firstly, we are seeing HADR log block group commit, which is starting point for synchronization. A log block ID is something like ending with 7920. Then, log is being pushed to log pool. At the same time, this log flush is starting. Then you can see HADR capture log block with 4 modes. Finally, log has been sent to secondary. At the same time, we can see log flush to disk completed. Now let's see what is happening in secondary replica for this log block. This is secondary replica side data. As you can see, log block ID is the same. First, we are receiving the log block. Here you can see log block decompression. However, log block is not compressed in our case, as you can see it is false. Therefore, I can say even log block is not compressed, SQL Server logs decompression related logs, which you can ignore. Then we are going to apply log block. After that, log block is being flashed to disk and it is completing here. Then with the three modes of hardening, this log block is being put to the HADR queue and its acknowledgement is being sent to primary. As you might pay attention, log block ID is changing after flashing the log to disk, which is expected. You might ask how you can correlate these IDs to this ID, right? So for this, we should go to primary and see wait log block and hardened log block ID. Okay, secondary sent back acknowledgement and it finished its job. Let's go to primary now. You can see here receipt of acknowledgement. After the transaction commit is finishing overall, we can see here second HADR group commit, right? This is processing time, which is microseconds. This shows how long overall one transaction log block took time to be committed with synchronization. Basically, this is just timestamp difference between first hardened and second hardened events. This shows the overall latency. The less, of course, the better. Then you can see next log block ID is started to be committed and it also follows the same path. Now we have been able to track the whole synchronization with a real example. How do we utilize it? Basically, we just compare timestamps and see where the latency is happening. For example, if we subtract send complete timestamp from receive timestamp, we get primary to secondary network latency. In this way, you can spot where the latency is happening, networking or disk. If you want to go deeper, you can check processing time of each steps in the event. We insert calculated latencies here from previous slide, okay? Here you can spot any big latencies and target the step where the latency is happening. One important point, here commit time is aggregate of all these steps where we are subtracting timestamp of first commit from second commit timestamp. However, as you might have spotted, this total time cannot be easily calculated by adding all this processing time because some steps are carried out in parallel. For example, log block flash and push to log pool and send to secondary can be done in parallel. Therefore, you cannot sum easily. But if any of the steps latency increases, it directly impacts the overall commit time. For example, if disk latency increases in the primary, it will directly impact overall latency like this. Now we understood how to track and calculate latencies at very low level. However, as you might have noticed, calculating latencies in this way might be a little bit time consuming. Therefore, Microsoft engineers developed AgLatency tool which does this calculation for us. You can access that tool by going to publicly accessible page and downloading the tool. Then run this SQL statement from both primary and secondary. And save the result as primary XML and secondary XML accordingly. Then we run this script by enabling the tracing. This is the same script which we already run, okay? Then start tracing and run it around 10 minutes. After running the trace for 10 minutes, you just put the event files correspondingly to primary and secondary folders. In the primary, we have primary XML and event files from this replica. In the secondary, we have secondary XML and related log files from secondary. Now we start the tool and insert these locations respectively and run. The tool gives such kind of output. Okay, what does this mean? Microsoft called disk latencies as local flash. Primary send and receive cover these events. Remote harden is the time spent sending log blocks to the secondary replica and receiving the associated LSN harden message back from the secondary replica. Also, there is commit time where max of primary local flash and remote harden is chosen. This helps to identify the average time for transactions to commit on the primary replica. Secondary receive is the processing time of receive block message. There is also secondary send, which is processing time of sending acknowledgement back to primary. Finally, aggregate of all the processing time in secondary is secondary processing. Now you understand this graph. From here, we can see that primary harden, primary commit, and secondary processing time is very high. There is a latency here. So, what is the issue here, right? We can also see flow control is also being triggered often. So, let's go back to the diagram. Our findings showing that the remote harden until here, right, is high. As a result, total commit time in primary is also very high. At the same time, we found out that the secondary processing during this range, right, is also high. This means that remote harden is increasing because of high processing time. Okay, high processing time in secondary. So, this means that we should investigate why secondary is taking time the logs. I mean, why it is taking time to process that transaction logs. Okay, the issue might be in different steps like receiving, blocking, decompressing, applying log block, any step of this. We should find out the processing time each of these steps and find where we are stuck, right? Often this kind of issue happens when the secondary does not have enough CPU to process the high load. Okay? there is the number of CPUs in primary is high, for example 2, 3 or 4 CPU, but in secondary only 1 CPU or 2 CPUs is there, so therefore secondary cannot catch up with the primary. As a result, secondary processing increases. In this state, what we can do is to add more CPU to secondary so that secondary can catch up with the primary. I hope you find this session useful. If you have any questions or suggestions, please kindly let me know in the comments of this video. I'll be happy to help and answer. Thank you for your time and have a nice day ahead.